All right. So today for the third lecture, and please excuse the occasional talking. We're going to be talking about non-fossil fuel energy sources, right? Continuing on our discussion for electricity generation from fossil fuel sources from last class. Okay. Um, this is the same figure that we showed last time, uh, showing all of the power plants in the US. Well, the current power plants, this figure is like a couple years old, so there's probably uh, a little bit of a difference with power plants either coming online or power plants retiring. But for the most part, this is what it looks like. And today, we're going to be focusing on mainly renewable sources of generation, as well as nuclear, which is why we're saying non-fossil as opposed to just renewables. And those you can see in this chart here in gray, which is wind, pink, which is solar. We're going to look at hydro, which is in green, and then nuclear, which is in orange. One of the things that you'll notice for nuclear in California, where we are, there's actually only one orange dot that's located right here. Hopefully you guys can all see my cursor. In San Luis Obispo, that is the Diablo nuclear power plant. It's the only plant left in California. It was originally actually slated to be retired in 2025, but they actually extended very recently decided to extend its operation, and so it's going to be around for a couple years further. Besides that, one of the things to kind of look for is the kind of regional location of the renewable resources. And so you'll notice there's going to be a lot more pink, which is solar, kind of on in the southwest, where you have a lot more sun. For wind, you'll notice that most of the wind generation is in kind of the Midwest all the way down to Texas. That's all the gray dots. That's where the largest wind resources are. And then you'll notice up in the Pacific Northwest, you have the majority, most of the power generation in that area is coming from hydro. They have a lot of that resource there. And we're going to look at some of the resource maps later on in today's lecture. So you'll see kind of why that arrangement kind of naturally makes sense. Okay. So the first resource we'll be talking about today is nuclear generation. So you may remember this figure from last class as well. So this describes essentially when power plants were constructed in the US, and the size of the bar indicates like the capacity that was installed. You can see that right in the 2000s, as we discussed last time, you have a lot of natural gas, and then more recently, we're building lots of green and yellow, which is wind and solar. But for nuclear, you'll see that most of nuclear generation was built basically between the 70s and the 90s. And there really hasn't been much nuclear built since then. And so if you think about the implications of like nuclear generation fleet as it exists today, that means most of the resources are what, 40, 50 years old. So that's starting to creep up to the sort of lifetime operation of a lot of these generation facilities. And so that means you're either going to have to retire them and replace them with new resources, or you're going to have to upgrade and retrofit them, um, because there isn't much sort of other nuclear power that's being built to replace that. And we'll talk a little bit about why that is and sort of the economics and political situation behind nuclear generation. But generally speaking, that's why, right, you don't see any of these red resources happening a little bit later on. And if folks are just joining, as I was kind of explaining earlier, feel free to chime in if you have any questions. You can either raise your hand or just type it out in chat, and I'll try and keep an eye on that. Okay. So there's actually two types of nuclear reactions. There's fusion and fission. All of the electricity generation that we do from nuclear power plants all happens with fission, not fusion. So fission is where I take an atom and I split it apart, and you get a net gain of energy from doing that because you actually lose mass. And conversely, with fusion, that's combining atoms together. You lose mass and get a bunch of energy as a byproduct. Fusion, not fission, is a technology that is kind of perpetually in R&D. The joke is like it's always 10 years away. Even 10 years ago, it was 10 years away. Today, it's still 10 years away. There are advancements in that field that continue to happen, especially at the sort of laboratory scale. But turning that into a viable technology that can produce electricity in a stable manner, but also right economically, compared to a lot of the other resources that we have to generate electricity, that's still a whiles away from happening. Okay, back to fission. So if you take uranium and you hit it with a neutron, it can produce this reaction where it splits the uranium and it releases additional neutrons, right? And so that reaction produces a huge amount of energy. And note that those three neutrons can then go propagate this reaction further. So you have this kind of chain reaction. And the amount of energy that you get from this type of reaction is absolutely orders of magnitude higher than the types of things that we get from traditional combustion, right? So just 1 kilogram of uranium produces 24 gigawatt hours of energy, which you would need, tons and tons and tons of coal to produce this equivalent amount of energy from combustion. As far as fuel resource availability, this is kind of a older map of what that looks like. So the map may look, slightly different from today, but generally speaking, your resource availability generally looks something like this. So total amount of uranium resource around the entire globe, 3.5 to 6 million tons. And we use approximately 27 tons of raw uranium fuel for a 1 gigawatt reactor over the course of a year. So a 1 gigawatt reactor is probably on the small side of a typical sort of nuclear plant. And note that these things are usually run fairly continuously. One of the things that I don't think I talked about in lecture two is the ability for different types of fuel resources and electricity generators to respond to electricity demand. So if you think about like a coal plant that needs to like boil water versus a natural gas plant, which just sends air through the turbine and combusts the gas, right, in the combustion chamber, that's a lot faster to ramp up and be able to produce electricity than it is to, heat up water um, and boil it to power a steam turbine. And for that sort of technical reason, with a nuclear plant, right, it's actually hard to get, it's actually much slower to get a nuclear reaction kind of up and going, and then boiling water. And as a result, nuclear plants typically don't like to shut down very often. And so kind of the point of this, going back to the second point here, when you're running this reactor, you basically have to keep it on the entire year. So that's why you can be sort of fairly accurate with the predictions of the amount of fuel that you're going to use in a nuclear reactor. Okay, how does a nuclear power plant actually work? If you look at this diagram, you'll notice that it actually looks fairly similar to a coal plant. And as I mentioned in lecture two, right, the way that we basically produce electricity is we get something to spin, right, and we operate that. We spin a turbine in order to um, get electricity out of a generator. And nuclear plants operate with steam turbines just like a coal plant. And so you'll notice the sort of right-hand side of this diagram is almost exactly the same as the coal plant, right? We have steam at a high temperature passing through this turbine to generate electricity. And then to cool down that steam, you have a condenser with a separate water loop, right? And again, as a reminder, the reason why we do this is that um, you can't really have dirty water going through the turbine. That would increase the amount of maintenance that you would need to do. You can contaminate the turbine with materials in the water. So generally, you want that loop to be as clean as possible. And then the condenser, that can be the source of continuous water that is coming from like some kind of reservoir. It can be from like a local river, that type of thing. And that is the water that's actually going to be coming um, out of the steam output from the plant. You'll notice on the left-hand side, this is a little bit different, right, from the coal plant, where the steam was generated from the heat to essentially boil the water and create steam. That's not coming from the combustion of your coal. That's coming from heat from your nuclear reaction. And so in your nuclear reactor, we actually have a third, or I should say, a second closed loop, um, and that water goes through to heat the water for what ultimately goes into your steam turbine. And one of the reasons why we have a separate closed loop here, right? Maybe this is kind of obvious, but um, the water in the second closed loop is highly radioactive. And so we do this so that you're not sending, radioactive material through your turbine. That would make maintenance of that part of it a lot more difficult. Okay. And so that's kind of high-level technical elements of how a nuclear plant works. And as I was kind of mentioning, um, there haven't been sort of very many new constructions. And in fact, a lot of nuclear plants are starting to reach an age in which they are supposed to retire. And so there have been, as I mentioned, like retrofits and upgrades, renewals for licenses to keep those going. And you can kind of see what that timeline looks like in this plot. Um, why haven't new nuclear plants been built? Well, one, very high capital costs. So the economics aren't very favorable for building nuclear plants anymore. Um, and in fact, the build time for a lot of these generators is so long that you get a huge amount of uncertainty where you could invest a lot of money, at the beginning, and you run into a variety of types of issues as it's being built, and you may have to, abandon it um, before it's fully constructed, and you could be, billions of dollars in the hole. And so it can be tricky to even get folks who want to invest in this type of infrastructure. Uh, in addition, one of the things that has driven the economics of it to be very high is permitting issues and ability to construct these things can vary quite a bit in different regions, and that can drive up costs. The other one, NIMBY opposition. So that is NIMBY, for those who don't know, stands for not in my backyard. Um, so there's definitely some fear, I would say, of nuclear power as a resource, right? We think about like nuclear explosions and radiation and those types of things. Even though, technically speaking, nuclear plants are like by far like one of the safest power generating resources. In fact, uh, in terms of like deaths per amount of electricity that you produce, I think nuclear is like far and away the best. They are in terms of radiation, which people think about a lot. Actually, the least radioactive place that you could find on Earth is actually inside of nuclear power plants because they have so much radiation shielding. And actually, compared to something like a coal plant, the background radiation is much, much lower. But that having been said, right, the general population, you typically have like a hard time convincing folks to want to have a nuclear plant near them. Um, there are Even though nuclear power plants are technically essentially zero emissions, right? You don't have any byproducts from something like a combustion reaction. The nuclear reaction does generate nuclear waste, but it's from a climate change perspective in terms of greenhouse gases. You have these alternative resources in wind and solar, which have gotten sort of increasingly compelling, increasingly competitive over time, whereas nuclear has become kind of like decreasingly competitive over time. And so, yeah, that's one of the other reasons, as we need more electricity and need to build more generation resources, people turn to things like wind and solar before nuclear power. And then the last one, right? The sort of disaster factor. After Fukushima, there was actually a really big shift away from nuclear in many parts of the world, not just in the US. All right. Any questions about that? or
I'm
cons?
actually confused with the definition of the chart. Uh,
Okay.
a reactor without license renewable. Can you elaborate a little bit more? Like, what is the without license renewable, and then what is the with license renewable? What's the difference?
Yeah. So the license renewal, so that these are basically licenses that you need to operate a nuclear power plant. And so what happens is, let's say, Diablo in California, they decide, let's say prior to the recent change, but they decide, okay, we're gonna retire in 2025, and so I'm not gonna seek um, any license renewal. And so what that means is that basically all of the light brown or tan uh, bars means that those are nuclear plants that are scheduled to retire. The brown ones are the ones that are scheduled to retire, but have actually asked for a renewal of their license so that they can operate longer. And then the green ones are um, reactors that have already gotten license renewals out to a particular date.
Thank you.
Yeah. And then did I see? Oh, okay. I see another question. In terms of electricity cost generated, nuclear is much more cheap than wind and solar plants. I don't think that's quite true. Um, in terms of in terms of electricity, um, like the marginal cost of producing electricity, nuclear is like very close to free. Essentially, you need a very small amount of fuel. So the fuel cost of producing the electricity is extremely low with nuclear. Um, And then with wind and solar, it's free, right? You don't have to pay for the wind and sun that you're getting. Um, when we think about the sort of cost, the total cost, this is something that we're actually going to cover a little bit later on the energy economics and sort of financing lecture. But we have this thing called levelized cost, which is you think about the total amount of electricity that you could produce over the lifetime of your generator. Um, and you take the total, so you take the total cost that you have to spend over the lifetime of the generator, not only to build it, but all the fuel and maintenance and everything. Um, that is, you take that and you divide it by the energy produced, and you have what's called essentially a levelized cost, which tells you um, essentially how much it costs to produce electricity, including the like distributing the cost of the capital over the lifetime of that resource. And then you can kind of compare better apples to apples, like the bang for your buck, essentially. Um, and so I can't remember off the top of my head, but I'm fairly certain with the high cost of nuclear these days that it still is more expensive. The levelized cost of nuclear is still more expensive than solar and wind. Although we'll see a figure of that maybe even in this lecture um, that will verify that. Um, okay, another question: what factors controls license renewals? Um, Yeah, I don't know exactly what goes into it, but I would imagine so. Part of it is that there are specific standards around um, uh, like age of some of the equipment that relate to safety standards and operation. And there are certain checks that they have to do on the infrastructure to make sure that everything's functioning correctly and will be within some kind of margin. and that it can function out to, you know, a certain amount of time. And so the Nuclear Regulatory Commission will look at all of these things to ensure, basically, at the end of the day, that the generator can operate as it's intended to, and that it can do so safely. Um, the specifics of which I'm not going to be so familiar with, but those are the things that they're going to be looking for to grant a license. Okay, so that is the one uh, non-fossil, non-renewable source that we're going to be looking today. And the rest of the stuff is going to be other non-fossil sources that are all renewable. Um, so we've got a bunch of different energy sources that are derived basically from the energy of the sun or from the energy contained within the earth. Then the reason why it's renewable is essentially you have basically an infinite resources. You're not depleting the resource like you are with fossil fuel or even with nuclear, hence the renewable term. We are not going to cover all of these today, but we will cover sort of the biggest ones, so solar, wind, and hydro. Um, I can speak a little bit to things like biomass, ocean, and geothermal, but you know, as of today, those are sort of fairly small resources being used, particularly in electricity generation. So hopefully you guys have kind of all heard of these in some way or other, but if you want me to go into a little bit more detail on the ones that we're not covering, feel free to ask questions if you're wondering anything particular about them. Um, right, we know that renewable energy is important. It's one, sustainable, and two, a lot of it is going to be a lot cleaner than our traditional power generation, which is usually like combusting fuel sources. And so we think about this as one of the like major greenhouse gas emission reduction strategies. And I'll mention that like uh, you know, in the climate change mitigation battle in general, right? Um, Electricity contributes a lot and has historically contributed a lot to climate change, but fortunately is actually one of the ones that we kind of have the best solutions. And I'm not going to say like it's easy, but it is one of the easiest solutions. Um, and kind of as a result, we've seen that it's being used and expanding at a really rapid rate. There had been a lot of like policies that support that. But nowadays, actually, a lot of it is kind of sort of purely on the economic side driving growth in this area. So why is it good? Right? Non-depletable, so sustainable, widely available. Now, as I mentioned, it's becoming more and more economically competitive. Um, it can it can produce electricity, heat, and in some cases we can even think about creating like sustainable fuels to replace fossil fuel application technologies. We use it for big cuts in greenhouse gas emissions and deep cuts in deep reductions, potentially in things like petroleum use. Okay, some bigger barriers, generally higher costs, but as I said, getting increasingly more economically viable. Like wind, for example, is economically competitive with basically most electricity production resources even today without any subsidies. Um, different types of environmental impacts, right? Just because you're not combusting doesn't mean the like construction of infrastructure for that resource uh, doesn't produce greenhouse gases or other sort of environmental effects. And so we do need to think about those as well. Uh, this is a big one. Integrating renewables into existing energy systems can be challenging. We talked about like intermittency a lot, right? The sun doesn't always shine, the wind doesn't always blow, and so how do you deal with that in a system where like electricity basically has to be produced at the time where you need it? With biomass, there's a whole thing about interaction with other markets. We'll talk a little bit about this like later on in this class. But that is one sort of issue is you have these sort of competitive aspects of things like if you're doing biomass from like corn, are you going to use corn for food resources or energy resources, right? And so that has some effects um, on the market. And then lots of market entry, social institutional policy issues. So just to give folks kind of a sense, um, so this is, I'm trying to think here. This is uh, in the US, I believe, not worldwide. That's gigawatts. Yeah, that yeah, I would say this is for the US, and you can see kind of the amount of capacity um, in total. Oh no, thousands of gigawatts. No, sorry, that would be worldwide. I thought that was megawatts. So this is a worldwide picture of the amount of renewable power. Um, and then just in 2021, you can see the amount of capacity that was added on the right-hand side. And most of that is actually solar and wind. And just as a um, anchoring figure, right? Just as a reminder, the total amount of power generation in California is about 50-ish gigawatts is our sort of peak load. And we probably have um, a little bit more than that in terms of total capacity. And I'll note that, the thing that I was saying about nuclear earlier, about it basically always being on, um, as a reminder, that refers to the capacity factor. So if you have a capacity factor of 1, it means that your power plant is always on. If you have a capacity factor of 0, that means your power plant is never on. And so this is talking about capacity, but it's not always like a apples to apples comparison when you're looking at different sorts of resources, because the capacity factors can be different amongst different renewable different resources. Yeah, Afshan.
You just said like 50 gigawatt, the peak load in California. That's the kind of
Yeah,
estimate.
just rough estimation. Yeah.
I'm wondering like what kind of power plants we use here in California for the base load. Is there like natural gas or coal?
Uh, the actually, so it's kind of interesting to talk about base load. And so what Afshan is talking about with base load, it means kind of if you've got actually let me draw this. 1 second. Hop onto my iPad really quick. So if you have power or sorry, if you have demand that looks something like this, and so this is like uh 1 day, 2 days. Um, so this is power and time. Basically what you're looking at is when I'm over here, that might be like in the middle of the night, and then in the morning people use more power, right? And then going back down. And so this is like a cycle of 3 days. It looks something like this. And so you basically have to have power plants on to fill to fulfill the power here, the power demand. And so base load refers to stuff that's like down here. This would be power plants that are like always on. Okay, so the question the option is asking is, in California, what is the base load? And actually it's a little bit interesting to talk about base load in California, because actually there are periods of time where everything uh, almost everything is produced by solar. Um, yes, we do have so the most kind of stable power is coming from Diablo, the nuclear power, which I guess you could call as kind of your base load. Um, but California is a little bit different because the amount of solar is so high that um, there isn't necessarily, besides the Diablo nuclear plant, you don't really have other things that are basically like on all the time. But that's a fairly unusual case, and I think a lot of places are going to be moving in that direction kind of in the future. Uh, but yeah, California doesn't, I wouldn't really say has like a clear baseload generation besides the nuclear plant.
So you mean like during the day, our base load is even coming from solar, right? Like,
Yeah, but like, but I don't know if I would characterize solar as like a base load power, because it's like, well, okay, depends on kind of how you define base load, right? Like if it's just under the squiggly part and we call
mhm.
that base load, then yes, then solar would be base load.
Then like during the nights, like then you
During
need
the
to
night,
switch, like yeah, every night you need to switch all this, like even base load to the other power
yes.
source, right?
Yeah, that's right. And
Okay.
so at nighttime, your base load would be more like gas generation in,
Mm.
I mean, or even it's getting hard to define it in some ways. Like we might even say the wind power
Mhm.
is kind of the base load, and then you would have natural gas as kind of your dispatchable
Mhm.
load.
Okay. Thank you.
Yeah, I see the question is the chart about global renewable growth or just in the US. So sorry for the confusion. This is almost certainly global, because the amount of power is too high to just be the US. I feel like I got myself confused on that last year too. I should have a better label. Um, you can see the total amount of investment amongst all of the countries here. Um, Yeah, we've kind of surpassed the amount of investment in fossil fuels a little while ago, and so global investment in renewable power is actually quite a bit higher, almost double fossil fuel investments, and that was 5 years ago. So today that trend continues to grow, where fossil fuels going down and renewables is going up. And this can hopefully give you guys some sense of scale in terms of the amount of spending that's happening um, um, over the last decade or so across these different countries. And so US is up there. Um, I think only surpassed by China, which has really ramped up their renewable investments over the last decade or so. Most popular new power generating technology installed in 2021. You can kind of see what that looks like. And I think I really like the sort of bar chart on the right-hand side, which shows the difference in the types of investments that were made just a decade ago versus, 2 years ago. You can see back then a lot of gas and oil and coal, whereas today that amount, in coal is basically nothing. It's not really competitive anymore, especially against gas. Whereas, a huge amount of solar, hydro, and wind, right? This constitutes what is this like 80, a little less than 80%, 75% or so of the generation today being installed today is wind, solar, and hydro. Um, Variable renewable energy, referring to solar and wind, looks something like this. Again, a lot of these charts are kind of just driving home the point that the investment in these resources is large and continuing to grow over time. Nevertheless, important to kind of keep in mind the shares in the electric power sector. You can see what that looks like across our sort of primary energy sources on the left-hand side, where those end up going. You can see renewable energy still kind of has a little whiles to go in the electricity system and in our sort of end use sectors. This is a kind of handy chart if you need to go back and sort of reference what the breakdown is by sort of fuel types as it pertains to both end use and our electricity sector. Okay, so now we'll do like a little deeper dive into technologies. Hydropower. We'll start off with this one. So hydroelectricity generation. So this is kind of emulating one of the first charts that we looked at of basically when generation resources were installed. And actually this kind of mirrors that sort of trend where we see hydroelectric generators. The vast majority is built between like the 1950s and the 1990s. You can see most of that of those resources here. And so not actually as many built past the mid 90s. And if anyone has a suspicion as to why that is, you can speak up or put it in the chat. But it's actually a different reason, right, than the nuclear that we were talking about earlier, where it's like, oh, it's kind of too expensive. You're having these both economic issues, permitting issues that are increasingly making it difficult.
I would imagine that like all the places where you could put a hydroelectric generator have already been taken up.
Yeah,
And
that's it. Yeah, exactly. So if you look at basically any hydrological resource in the US, yeah, it's basically dammed and there is no sort of major source of additional hydro generation that you could really install and get a reasonable amount of power from at an economic rate. So yeah, most of the resources are basically damned already. When we look at people talk about solar and wind all the time, but actually for a long period of time, hydro is uh, one of the cheapest electricity generating resources, and actually generates more most of the renewable generation until sort of pretty recently. Like wind started to um, has just started to take over, right? But hydro can vary between depending on the region. Um, Across the entire US, you're talking about like six as up to as high as 9% of the total electricity generation. And if you're up in the Pacific Northwest, or if you're like um, in like the Toronto area, right, you're getting actually a much higher proportion, like 60% all the way up to 95% of your electricity coming from hydro resources. Okay, and in terms of potential, like where is the best places to kind of put it? Yeah, you can see in the Pacific Northwest, right, there is pretty good resources over here. Um, and so that's why you do have a lot of hydropower there. And kind of some in the Northeast as well, not as good as kind of up in the Pacific Northwest. But generally speaking, there are other places in the world that have like a crazy amount of hydro resources, and they do, and those places do take advantage of that. And this is, this measures essentially runoff, meters of annual runoff as a way to kind of capture the hydro potential. So theoretical hydropower resources, the maximum energy carried by water runoff on land, right? So after it rains, it collects and then goes some amount, and you can take advantage of the potential energy from wherever it lands down to sea level. Global theoretical hydropower is estimated to be between 16,000 and 40,000 terawatt hours. But of course, and that's purely kind of a function of like the geography, right? And the amount of rain that you're getting. But a lot of it can't really be sort of captured. You might not be able to access like the flow of water, and there might be other sort of siting issues. But that's kind of just to give some perspective of like the total amount of energy that you could get. One of the things to keep in mind, yes, hydropower is dispatchable in some ways. And it's limited in sort of other ways, right? And so unlike solar and wind, in which you are kind of just like at the mercy of whenever you have sun or rain, or sorry, not rain, wind, sun or wind, um, the the amount of energy that you can get from a hydro system isn't intermittent in the same way, but it is affected, right, by sort of precipitation, which can vary over the year, right? And so in different seasons, you may have a lot more rain than others, and that can affect your ability to have to operate your plant in certain ways. And it is also affected by precipitation patterns across the years. And so if you lived in California in over the last decade, uh, you'll have lived through several drought periods actually, and during these drought periods, the electricity production from your hydropower resource actually diminishes in your drought years. There's less water that goes through, as well as your sort of potential energy that you can get from the water might be lower as water levels decrease. at the end of the day, still operates by spinning some magnets, right? And so we have a turbine that utilizes water pressure from having a potential energy difference in your reservoir compared to the outlet level of your hydropower facility. And so the operation of this is actually fairly straightforward. You essentially send water through your facility, which spins a turbine, which will power the generator, right? And allow you to create electricity. Um, the power that you generate from hydropower plants can be calculated in using this equation. Power is equal to the turbine efficiency times the density of water times your gravitational constant times what's called the head, also height, right? It's basically the difference in height between your inlet and outlet, and Q flow rate. And so actually, if you think about what this actually looks like, this is basically a reflection of your potential energy equation, right? So potential energy is equal to mgh, mass times gravitational constant times height. And so to go from energy to power, we divide by time. And so that's where your flow rate comes into play, right? And so you have divide by seconds here, but otherwise your mass is density of water times the amount from the flow rate, so meters cubed. So you have your mass M times G 9.8 times H, right? And so easy way to remember it, you can always derive back to power from the potential energy equation. And we don't capture 100% of the energy, which is why we have this term here, the turbine efficiency. And for hydro turbines, there are different types of turbines. We're not a mechanical engineering class, so we're not going to like get into the details here. But basically, the idea is different types of turbines can handle sort of different types of conditions in your hydro facility. And so depending on the construction of your facility and the water resource, you might put a different type of turbine, right? And so turbines can handle different pressures generated by height differences, right? The head, as well as flow rates of your water. And so this kind of shows you this kind of logarithmic scale of different types of turbines, technologies, and the conditions in which they are sort of optimally set to operate. And so, Pelton turbines can handle these large height differences. And you can, whereas, Kaplan turbines are typically for, smaller ones, and then things with high flow rate, you might want like a Francis turbine. Yeah, and so the efficiencies are going to depend on the type of turbine that you use, as well as the conditions of the water from your reservoir. Okay, and so that covers hydropower. And if anyone has any questions, feel free to speak up or type in chat. Since we're doing our online lecture, I know it can get kind of tiring over time, so I like to have a little break halfway through. So let's take a quick, let's say a 4-minute break until 1:10. I'll stick around if anyone has any questions, again, about anything that we've covered, but we can take this time to have any like class questions as well. But in the meantime, just if you need to use the restroom or anything, we'll do a quick 4-minute break until 1:10.
Hey, Alan, I had a question, sort of as it relates to nuclear reactor retirement. I remember reading a while ago that when Germany retired their nuclear fleet, they were expecting all the power to be, or the energy demand to sort of be taken over by renewables, but it got taken over by natural gas instead.
And
Is that,
coal.
oh, and coal. Okay.
Yeah.
Is that something we see sort of across the board still with nuclear retirement?
Yeah. So the thing about nuclear, right, is that nuclear power plants are like really, really, really big. Um, and so you're talking about replacing like several gigawatts typically of like continuous power. Um, and so the hope is, right, is that you want to replace that source of clean energy with other sources of clean energy. And so a lot of times, the commitments are, hey, we're going to replace it with renewables. Um, but unfortunately, like due to the intermittency, um, and if you're behind the schedule on like deploying that amount of capacity, you got to replace it with something. And so, yeah, you do see replacements of those resources, especially in the short term, often fall back to fossil resources. Um,
Thank you.
yeah, in the longer term, I would say like Germany, like they retired all these nuclear power plants and then they got slammed pretty hard with like replacing them with fossil resources. But actually in the long term, it's the trend has been good. A lot of that power generation has since been, more renewable resources. And so um, over the long term, we have seen um, I would say better trends with these retirements. Oh, okay. I see a question from Madhu. What types of turbines are mostly used in the US? Both. Uh, there are both impulse and reaction turbines. I don't know specifically if there's like a majority or preference for one or the other, but I do know that both are fairly common. Okay, so let's continue onwards. I think I have like way too many slides to get through still, so um, let's see. Wind power, our next one. So starting off with economics of this. So this is like one of the classic cases of uh, really sort of big improvements over time and kind of this like bet by government and public policy that like, hey, we're gonna provide support for this thing. The technology is going to come down in cost, and that's actually exactly what we saw. And so, from the 80s to the early 2010s, you saw a 10x price decline in the price the capacity deployment cost essentially. Um, and that has actually continued to decrease to the extent where we think about the cheapest power to deploy in the US as kind of being natural gas historically, like in the 2000s. And now wind is at that or even lower in a lot of places. And you can see that reflected on the right in terms of cumulative capacity. Continues to grow. And that is one at the beginning due to like strong government support, right? They provide types of subsidies in some ways, or there's like requirements to build renewables in RPS, renewable portfolio standards. But now kind of just because like if from an investor standpoint, it's like it's basically the cheapest electricity generation infrastructure. One of the cheapest. Okay, if you remember the chart from the very beginning where I showed, oh, most of the wind is like in the swath from the Midwest down through Texas. And why is that? Well, their wind resource availability. If you look at these, so the way this is done is they look at the speed of wind at a 100-meter height. And you can see that purple is the like really good stuff. Or actually blue is the best. But blue, then red, then purple. And a lot of that is located in the Midwest, where we see a lot of the wind resources being deployed. There's also what's called offshore wind, which is if you build turbines in the water off the shore, hence the offshore. And you can see that those resources are really, really high, particularly right in the like Oregon, Northern California, and then out in the Northeast. And so those resources more recently have been sort of heavily developed, and not only that, those tend to actually be higher capacity factors, so they'll be let's say on more often than their sort of onshore counterparts. Okay, so kind of just some numbers to help crunch here. So a good wind resource, you're talking about energy from energy from the wind itself, the kinetic energy of wind. You're talking about like 500 watts per meter squared. And so if you, so this is if your wind is blowing at like 7.5 meters per second or 17 miles per hour. And if you can take that kinetic energy, like a quarter of that kinetic energy, 25% efficiency, you get 125 watts per meter squared. And so per meter squared, right, of a turbine, you're talking about on the order of 1,000 kilowatt hours production per year. And so if you think of this as like the size of a rotor of like of your wind turbine that needs to power your conventional house, you would need a 24 meter squared rotor for your house, right? And so let's see, if you square root that, right, you're talking about like a 5-ish meter rotor diameter. To fuel your car would be something like 6 meters squared. And then you have like a typical wind farm spacing of 5 rotor diameters by 10 diameters. That can give you a sense of like the size of your space that you would need for a wind farm. And so there's like you can kind of use this to get some idea and calculate the amount of space that you would need, right, from a wind farm to power a certain amount of energy demand. It's actually one of the questions on the homework.
Is 17 miles per hour the speed of wind that you
Yeah,
want? The speed of the
yeah.
rotor?
Speed of the wind. Yeah. Okay, so wind turbine, same as everything else. You get something to spin, you can make electricity. And so in this case, the actual turbine is that whole thing. You've got this gearbox and nacelle, but this is the nacelle is the actual housing that contains the gearbox and the generator. So the turbine is spinning via the wind, generates electricity, and you send it down like so through the tower. Yeah, if anyone's actually been inside a wind turbine, they're actually like quite a bit bigger than you think, or than I think originally. And they're very tall. If you want to do like maintenance on one of these things, you got to climb like endless series of ladders inside. Um, Okay, so the maximal theoretical efficiency that you can get is about 60%, but the average typical efficiency is 35% to 45%. And when I'm talking about efficiency here, right, we're talking about there's like some wind, the wind that's passing through the rotor blades contains some amount of energy, kinetic energy, then you can capture, 1/3 to 1/2 of that kinetic energy. Um, where does the rest of that go? So, um, if you if you take one of those like handheld little fan things that you can blow, right, and watch it spin, if you hold your hand behind it, you'll notice that you'll still have some like wind energy from your breath hitting your hand. It won't be as much as if that thing wasn't there, right? But so you don't get to capture all of the kinetic energy moving past that wind turbine. We build these things pretty high because the wind energy tends to be higher at greater heights. And also because you need to have the blades be able to spin without hitting the ground. So similar to the whole thing with the hydropower, the wind energy you can calculate based off of our equation for kinetic energy. So 1/2 mass times velocity squared. So you can get the mass of the wind, which is just the surface area that the wind is passing through times the velocity times the density of air, and that'll give you the mass, right? And times time as well, because that you need to know, how much air actually flows through. And so that's the wind energy equation. And if we wanted the power, right, you just divide by time. So you could divide, that would cancel out the T term here. And so you have power equal to 1/2 area times rho times V cubed. All right, these things are big. We think about yeah, when I was, first getting into like the energy field, the like really big turbines we talk about as like the 3 megawatt turbines that are 100 meters high. But now we regularly talk about 5 kilowatt turbines and even larger, especially for the ones that are offshore. Those things can be, yeah, quite large, right? And so here's for comparison, right? Your Statue of Liberty, Eiffel Tower, Empire State Building, right? So these things can be absolutely massive and generate, quite a lot of electricity, right? So a single turbine at 3 megawatts, if you have an entire wind farm, yeah, you can generate a pretty substantial amount of electricity. As the turbines get bigger, I mean, the reason why we're building them bigger is you get a larger capacity. That should follow right from that equation, right? It's a function of the rotor diameter, so the amount of energy that you're capturing increases with the size of the rotors, and so your nameplate capacity increases as your rotors get bigger and bigger. One of the other things that has been a product of the locations in which we're deploying them, but also as a function of the technologies themselves, the capacity factor, right? Which is, again, in reference to how often it's like on, and actually the amount that it's on has increased over time pretty consistently. And so back in the early 2000s, you're talking about capacity factors of like 20 to 25%, which is quite low for today's standards, right? So now we're talking about capacity factors of 35 to 50%. Yeah, which means that you're generating basically double the amount of electricity from 20 years ago. The amount of capacity additions is tremendously large. So across the world, you're talking about 600 gigawatts of capacity additions. Now, remember that the capacity factors of these things is not 100%. And so, compared to the different type of resource, again, you need to think about the apples to apples comparison. But generally speaking, right, this amount of power generation is like on the order of, the amount of power that you're it's on the same scale as like the total amount of generation resources in like the entire country. Cumulative offshore wind capacity looks like this. So again, offshore is the stuff that's being built out in the ocean. That is not as much as onshore wind, right? There's like logistical difficulties of like being able to set up this wind turbine out in the middle of the ocean, but that has been continuously increasing, right? The trade-off here is that you get a lot better wind resources when you're building these things out there. And so typically the wind turbines are like way bigger that are getting built out in the middle of the ocean. This figure is a little bit older, but 5 or 6 years ago, or I guess we're 2024 now, so 7 years ago, this is where we stood. UK and Germany have the most. Denmark and Netherlands, like per capita, have I think some of the highest in the world. But again, that construction and infrastructure deployment continues to grow over time. Okay, so that covers our wind stuff. Any questions about wind resources? Okay, moving on. So solar, kind of the natural complement to wind power. So starting off again on the sort of economic side, right? The more we install, the better we are at developing the technology, building it, and deploying it. And so costs have come back down over time, not to the same extent as wind yet, or let's say it's not like as competitive, and the capacity factors are lower, which makes it doubly harder. But nevertheless, right, you're still talking about a sort of 4x decrease in price over the last decade or so. And I would say the relative amount of growth in capacity deployments is actually largest for solar. So where does the energy come from for solar, right? From the sun. You have solar irradiance. And so this is kind of a figure of like what happens to essentially sunlight, right? So you have coming through the atmosphere, some of it gets scattered back into space. Some of it gets absorbed in various layers of the atmosphere before you get some being absorbed by your surface or reflected back into space. And so we take advantage of the stuff that comes down to the surface. And that's essentially the energy that you want to try and capture. And again, this depends where you are on Earth. The amount of energy coming from sunlight hitting the surface varies, and it also varies throughout the year, right? The angle of the Earth as it relates to sunlight coming in through the atmosphere is different, and so you could have, higher energy at some points and lower energy at others in the year. Right, and so same as I was just saying, atmospheric conditions, time of day, time of year, and even solar cycles actually can influence the amount of energy that you're getting. Okay, compared to any other source of fuel that we've looked at, the potential energy from solar is huge. Like, it completely dwarfs all other fuel resources on Earth combined by many, 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 many orders of magnitude. And so the total energy that you're getting, we'll say, on the sun hitting the surface of the Earth is about 1,000 watts per meter squared. Right, and so after you account for weather, night and day, seasonal variations, that number ends up being, on average, about 170 watts per meter squared. So if you count all of this up, you get 3.9 million exajoules per year, which again is like way larger than all fuel resources cumulatively combined, orders of magnitude. And this is like annually, right? So you could do this again and again. Whereas even if we were to use up all fuel resources, it wouldn't even come close to this. But so most of that is over the ocean. So we don't really build solar panels over the ocean. So if you scrap all that, you're talking about on the order of like 0.8 million exajoules per year on land. Yeah, and so just to give some sense, okay, I had some relativistic scale here, right? So 1 hour, all of the solar energy hitting the Earth is the same as all energy consumption by human activities in 1 year. Okay, in the US, the solar resource, where's that most sort of available in the Southwest, and so that's why in the earlier picture that I showed, or figure that I showed on location of power plants, right, most of the solar resources are in the Southwest, and that is a really important consideration, right, for where you put the resource, especially on an economic. If you think about it from an economic standpoint, like if you are getting twice the amount of sunlight in Arizona compared to like Pennsylvania, then to get the same amount of electricity, you need to install like double, like twice as much, right? And so it costs twice as much. And so that makes a big difference in from like an investment standpoint. If I want to have like an economically competitive electricity generation, that will become location dependent. So worldwide, the picture looks something like this. Not too surprising for folks, I hope. And so you can see, relative to the US, there are places that actually have a lot of this, a lot more of this resource. And so you can see kind of the scale here on the bottom. It gives both a daily sum and yearly sum of the essentially energy density of the solar irradiation in different areas around the world. So, unfortunately for like Europe, it might be a lot less economic to build solar, even though they are doing it in many places, compared to, let's say, like the global south. Okay, we can do like a similar type of back of the envelope calculations for solar. Um, so insulation, so that's like the essentially the energy density, or not energy density, power density of the solar flux. So 1,000 watts, as I was saying, or 1 kilowatt maximum. And if we took that number and we saw how much energy that we could get out of it, so we convert at a 10% efficiency. And so that's kind of a conservative estimate, but unlike wind, solar is a lot less efficient. And so just back of the envelope, let's say 10%, make the numbers a little bit easier. 100 watts per meter squared. So your average annual insolation, instead of 1 kilowatt, we'll say 200 watts per meter squared at 10% efficiency. You're getting about 175 kilowatt hours per like meter squared of a solar panel in a given year. That's actually a little bit low, I would say, for today's standards, but back of the envelope, the amount of area that you would need to power a conventional house would be about 100 meters squared, which is actually kind of like the average sort of rooftop size-ish in the US. And then to like charge your battery car, you need like 20 meters squared. To fuel a hydrogen fuel cell car, a little bit bigger because of the efficiency losses, 35 meters squared. And so that hopefully gives some high level back of the envelope estimation of like the solar needs to power these types of demands. Okay, here's our one different technology. There's no moving parts, so nothing's is spinning. So, maybe 30, 40 years ago, I would have said basically all electricity in the entire world is produced from spinning something, right? But actually solar is kind of the most common one that is that's going to differ. It has no turbine, unlike pretty much every other technology that we've talked about today and from last lecture. And so the way this works, a solar PV, sort of solar photovoltaic cell, is you have sunlight that comes down and impacts your PV cell. And the energy from the photon will essentially excite and dislodge an electron, which travels on the surface of the cell. And that creates a voltage because you have a electrode differences. You have a negative electrode and a positive electrode. And so that electron wants to race through and go to the other side. And so you have current running through your wire. And that's how you get electricity. And so this actually operates in a very different way from our traditional power generation devices. You produce these cells by doping silicon with boron to create your positive charge, and silicon and phosphorus to create this negative charge. So the highest efficiency that has kind of ever been achieved, so I would call this kind of like a lab-based efficiency, right, is 46%, but most PV cells today, you're talking more on the order of 15%. I used to say 10 to 15%, but now I say 15 to 20%. So efficiencies do kind of incrementally improve over time as there's improvements of the technology, but nothing kind of revolutionary where you're getting like big jumps in efficiency. And so again, just to be clear, what that efficiency refers to is we think about that insulation energy, right? So like 1,000 watts per meter squared maximum that's hitting the surface of the Earth, we can capture, 15% of that total energy. Okay. The amount of energy that you get can also depend on the type of collector. And so even if you use the exact same PV technology, if you just kind of laid it flat on the ground, the angle at which sunlight hits your collector can influence it. If you think about, let's say, like if you drop a ball, or you throw a ball at an angle at the ground, right? The amount of force that essentially you want to be impacting it, you want to be like perpendicular to that to essentially capture as much energy as possible. And so if you just had it flat, the sort of relative amount of energy might look something like this in January, but if you had it kind of angled in a certain way, where you are trying to get, as much perpendicular to photons coming in on average as possible, you might look something like this, where the yellow is getting essentially more energy and blue is less energy. And then you could have something called like a tilt tracker, where actually the solar panel will move. So you are maximizing the amount of time that it's perpendicular. You could get something like this, right? And it's a trade-off, right? You can't always build these things. Like you wouldn't want to, like on residential solar locations, you typically don't see these tilt trackers, right? Because you'd have to put, pretty large motors up there to move the panels like on top of your roof. And the space that you would need to do that might not be ideal. And so these might better be suited for like larger sort of solar farms. But again, the point is here is that the angle plays kind of a big role in the amount of energy that you collect from sunlight. Okay. We talk about solar generation in terms of utility scale and in terms of distributed solar. So utility scale, oh, I see a question. Is the motor self-powered by the PV? Actually, I have no idea. That's a good question. I don't think it would be, although, yeah, I mean, you would almost, maybe it could be, but you'd almost certainly want like a backup power source, probably. Yeah, I honestly don't actually know the answer to that. Okay, so utility scale is like what we think of these like large solar farms where you have like rows and rows of solar kind of like out in the field. And there are pros and cons to like doing this versus like just putting them just on top of rooftops, right? And so we can talk about some of these, right? So on a utility scale, typically we can choose to locate these solar farms out in places where you're going to have the best sunlight, right? As opposed to distributed, you build them like where people live, which may or may not necessarily have great sunlight. So typically you're going to have higher capacity factors with the utility scale. And you can do things like you can build these like tilt trackers and that sort of thing, where that would be a lot harder to build on top of a roof. So you're going to get better energy density, better bang for your buck in that regards. And so from like a economic standpoint, like $1 per kilowatt hour, the utility scale is almost certainly going to be cheaper than the stuff that you're putting on top of your roof. However, one of the benefits is that it's located right where your energy demand is, and so you get to mitigate like things like transmission losses, which they're small, but they can add up. Yeah, and uh, there are other sort of benefits of distributed solar and distributed energy resources in general, where like you could, in theory, you could have these like microgrids where you're servicing um, um, much smaller areas than what utilities typically are trying to service or provide services for. Okay, net metering. Man, I should even maybe start getting a little bit more away from the sort of net metering, especially with what's happening in California. But what I would say that we're not going to get into some of the like complicated policy stuff with net metering, at least for today. But generally, it's kind of straightforward the way this process works, right? So you have solar on your rooftop, and you can produce electricity and you can use it, some of it yourself. And um, if you have more sunlight electricity than you are using, you can send it back to the grid. Or if you need supplemental energy from the grid, you can still draw energy from the grid to supplement what you're making from solar to meet your total demands. And so you have a meter that typically measures the amount of electricity that you use, but this time it's bidirectional. It'll be negative when you're sending electricity to the grid, and then it can essentially count up the total amount of excess that you've generated, right, and sent back to the grid compared to what you've used. And so this is a sort of program that that you can use to figure out your like electricity bill, right, with your utility if you have rooftop solar. There are let's say some complications in terms of the types of rates that solar homeowners pay now and likely will pay in the future, because of like issues with like fixed costs, and actually with the scale of deployments of the stuff in California, like in how that's affecting a lot of the fixed costs in like PG&E, that they have in trying to provide electricity for everyone, but then you have all these like local generation. And so net metering is a changing domain in California. And we can talk a little bit more about that in detail when we hit some of the policy stuff later on in the class. But it's a pretty interesting kind of development over the last couple of years about how you handle solar home, like home solar owners in the state. It'll probably be a good case study for places that are trying to have more and more of this in home solar in the future. So, when we think about solar power, I think that's a lot of what people gravitate towards, like this photovoltaic, either utility side or like on your rooftop. That's what we think about when we say solar, but actually there are other applications for this. So solar cookers have been around for decades now, and this is alternative means for cooking food. You can use this to collect the heat energy from sunlight, and trap that heat energy and focus it and concentrate it so it's hot enough to cook different types of foods. And like this is something that you this isn't something that you should kind of be dismissive of, actually. Like especially in third world countries, in certain third world countries, this type of thing can be a huge, important resource. It can save tons of money from fuel, and I mean like significant in terms of actually being like a sort of life-altering amount of money, where you're spending a third to half your money on fuel, and that becomes entirely savings, right? If you have something like this, it can be a huge thing for safety. Um, there were like issues 10, 15 years ago in places like Darfur, where women would have to go out and collect fuel for like cook stoves, and you could have bad things happening when they were trying to collect fuel. And so this can actually be a big improvement to human safety as well. Yeah, and so solar cookers may be kind of not really a thing that we think about in places like the US, but can make a pretty big impact on people's lives and other places in the world. Solar heating systems, so not using it to convert directly into electricity, but actually this is actually not too uncommon in California, where we have these solar collectors that actually heat up water for your hot water system. And so the way this works is it's not actually hot enough to get water to the temperatures that you would want for like hot water from in your kitchen, or for taking a shower or something. Let's say it gets like lukewarm, right? But the uh, but the amount of energy that it takes to heat up water is actually really quite significant, and so it can supplement your hot water system and really increase the efficiency, as you need less electricity or fuel to bring your water up to the temperature that you want. So these things actually make a really big difference in terms of money savings for heating water. One other big one is concentrated solar power, CSP. Okay, I said that solar doesn't use turbines like everything else does, but actually there is a form of solar that does. So this is a little bit different. It doesn't use photovoltaic cells. You just actually have these mirrors. And these are mirrors that are essentially in this ring around this receiver. And so you can see in the diagram here, they're all angled in such a way that they can point sunlight directly into this receiver. So it's a series of mirrors and lenses that focuses that sunlight into a really small area. And right, if you think about that experiment that you do as a kid with a magnifying glass, right, you can focus the sunlight hot enough to burn a piece of paper. That's essentially what this is on like a much larger scale, and they use that heat to boil water. And what can we do with boiled water? Well, we can send it through a steam turbine and generate electricity. And so this is a alternative form of solar, and there's actually CSPs in California and in other places in the Southwest. I think there's one actually near Death Valley. Anyways, so much smaller in amount, like total amount of capacity that exists for CSPs, but you can see what that looks like here. And Spain, for some reason, has decided that they want to deploy a relatively large amount of this technology. Okay. Oh yeah, Afshan, go ahead.
So, Anne,
Yeah.
do we have like other lectures on policies regarding renewable energies? Are there like where do we have a separate lecture?
Yeah,
Like
so
with
towards
respect to IRA and how much, like which
Mhm.
resource is gonna be how much
Yeah, so at the
target
like
years. Mhm.
so what we do, kind of at a high level, we're kind of going through a lot of the foundational like technology stuff and economic stuff. Then we'll
Mhm.
talk about sort of modeling tools, and then
Okay.
at the end of the course, we cover um, policies, policy modeling, and policy background. And so that's going to get into things like IRA. So we actually do have do we have an entire lecture on IRA? It's going to be combined maybe with like one or two other policies, but yeah, we'll definitely get into some IRA stuff later on.
Okay.
Yeah, but if folks have any particular questions as it relates to this stuff, whether it be about specific things with IRA, I'm happy to chat about it now. Okay. So decentralized versus centralized. So decentralized is what I was saying with distributed energy, and centralized is more of the like utility scale. So you can kind of see the relative amounts in share of installations, what that looks like here. And so more utility scale stuff over time. Okay, and so that actually kind of concludes the solar stuff, and we'll do, kind of like a high level reflections on renewables and renewable energy in general as we wrap up today's lecture. So renewable energy accounted for a little less than a fifth of global final energy in 2017. And that breakdown looks something like this with your breakdown of renewable energy, although maybe, okay, this is not, I should actually say renewables is 10.6%. This 18% is more like non-fossil fuels as opposed to specifically renewables. So the renewables that we're really talking about is this 10.6% here, which has grown right since 2017. That is wind, solar. This 2%, most of it is actually hydropower. From an electricity standpoint, because the other one is kind of all energy, but I think we're mainly focused on energy here. It's a larger share, so 26%, with most of it being hydropower at about 16%. As I was saying before, with wind and solar both growing pretty rapidly. Yeah, here's the economics. Okay, so this chart I think answers the question earlier about the levelized cost of different resources. And so it is a function of the total amount that has been installed over time. And so we can see that solar photovoltaics has been dropping, pretty dramatically. Wind as well, even lower than that. Whereas nuclear, right, which was cheaper, has gotten more expensive over time. They don't have nuclear gas on this chart. Or sorry, did I just say nuclear gas? Natural gas on this chart, which is going to look kind of close to onshore wind. And we'll actually have a sort of better figure with the ranges of LCOE estimates in the energy econ lecture. Okay, last bit to talk about, so environmental impacts. So like I was saying, with renewable resources, we think of these as like great boons for, the fight against climate change. But it is still important to consider the environmental impacts of some of these technologies. And so, really quickly, what are some of those impacts, right? So impacts and externalities of solar energy, land and water use, the concentrated solar power, right? The one with the mirrors, you need cooling water that can be scarce in a lot of the desert areas that it's located in. And generally speaking, putting up mirrors and putting up photovoltaic panels, right, requires a lot of land. And so you're talking about a kilometer squared for every 20 to 60 megawatts, depending on where you are and how efficient these things are. The materials required to build them can be pretty intensive, as well as the energy required to build them, and it uses hazardous materials. So that's one thing to consider. Environmental impacts and externalities of wind, the three main environmental concerns. So visual impact, noise, risk of bird collisions and wildlife disruptions. So important things to consider, right? So people often cite this thing about like birds getting killed by wind turbines, which is a real impact that you see. But people don't talk about things like um, the impact on birds from like coal plants is actually even higher than a wind turbine. And actually, there are some positive externalities too. So the closest large scale wind farm to Davis is actually in Suisun County, and not county, sorry, but Suisun City area. And so you can go and look at those. That they're actually co-located on farms. And when I went there during the summer, it was like really hot, and it was on a sheep farm. And so what actually happened was all the sheep on the farm, they would line up in the shadow of the wind turbine to cool down. And so wind turbines can provide shade for for these guys. So some positive benefits as well. Okay, lastly, environmental impacts and externalities of hydro. So large ecological impacts, right? So, you affect fish and other wildlife. And then there are issues with flooding, especially when you have like overflow and issues like that. Management of your reservoirs can lead to, downstream flooding issues. Yeah, and so again, these are important resources that we can have to have lots of the benefits that we would like, but it's important to keep in mind some of the like negative environmental impacts that can be associated with these things as well. Okay, so that concludes our lecture for today. Before you leave, one quick note: the homework is now posted, and so everyone should have access to that. Homeworks will be due not Monday, but the Monday after next. So you have a little bit less than 2 weeks. I will have my office hours, unfortunately, still online. I still need one more negative day before I can do in-person stuff. But that link is posted on Canvas, so you'll be able to find me there. Yeah, and otherwise, unless something crazy happens, again, we will have in-person lecture next week, and I definitely look forward to meeting you guys all in person and not doing this pandemic throwback thing. So thanks everyone for doing one more online lesson. I'll stick around if anyone has any like questions that I didn't get to, or if you have any like course questions, but otherwise I'll see you guys all on Monday.